Hi, I'm Bob Hanlon. I want to talk with you today about the E word, entropy. Specifically, I want to go into a brief background on how Rudolf Clausius discovered entropy in 1865, but then focus in on a specific feature of entropy, the fact that the entropy of an isolated system increases to a maximum. More specifically than that, I want to talk about who actually owned that discovery, who owned the discovery of an increasing entropy. Was it Clausius or was it Gibbs? Let's find out. Brief background. The concept of entropy rose from the back and forth efforts of Clausius operating out of Berlin and then William Thomson and also William Rankine operating out of Glasgow. This was in the time frame of 1850 to 1865. They both focused on Sadi Carnot's work back from 1824, his analysis of the steam engine. Carnot, if you remember, said that the steam engine behaves like a waterfall. You have a caloric stream coming into the engine, falling through a temperature from the hot source to the cold sink, and generating work by doing that. He spoke about the fall of caloric. In his steam engine, Carnot proposed that the work of the steam engine was equal to the flow of this caloric stream times the height of the fall, dt, times some unknown function of temperature, he called C. If you look at this, then the steam engine efficiency was W divided by Qn equals to this dt, the height of the fall, divided by Ct. This equation then led to the final steps along the path to entropy. Again, Carnot efficiency, and really Emil Clapeyron interpreted Carnot's work by putting the mathematics to it. W over this infinitesimal amount of heat coming into the engine is equal to dt over this function of temperature. In the mid-1840s, James Joule's conjecture was that this function of temperature was equal to temperature itself. In 1854, then, William Thomson then proposed that the work divided by the dt, the change in temperature, is equal to this infinitesimal amount of heat divided by temperature here. Boom. Symbols crash. This is the first time that dq over t appeared, at least that I can see. And it was this dq over t that led to Rudolf Clausius's next step. Clausius, first of all, proved that this function of temperature here was equal to temperature itself. He then studied the meaning of this dq over t term, studied it much, and until finally he concluded his studies in 1865 by declaring that ds is equal to this function dq over t for a reversible process. S then was equal to entropy itself, a new property to matter. He concluded his paper in 1865 with two famous statements. The first was, here's the German translation, the energy of the universe is constant. This led to the first law of thermodynamics. His second conclusion, again the translation, was that the entropy of the universe tends to a maximum. When I was reading the paper, this conclusion jumped out at me at the end because I really didn't see the prelude to his findings. I didn't see a lot of discussion about the entropy changing in a system at all. And as a matter of fact, I was rather shocked when I read this at the end of the paper because to me, it came out of the blue. And you would see that if you read the paper yourself. Let's look a little bit about how Clausius got there, though, at least my interpretation. In attempting to define the second law of thermodynamics, Clausius analyzed two transformations of heat as he saw it. The first transformation was the transformation of heat into work. The second transformation was what occurred when heat transferred from a high temperature to a low temperature. Note that these two are the early versions of the two laws of thermodynamics. He attempted to better clarify the second law of thermodynamics by stating that heat cannot of itself pass from cold to hot. Today we say that heat only flows from hot to cold and not from cold to hot. What he did out of this extensive study, though, was he introduced irreversibility and inequality into thermodynamics. It's really one of the first efforts to do that, and so that's where we get the less than or greater than signs in thermodynamics. And then he proposed that the sum of all of the heat transformations here must be greater than zero. And he went through logic on how he got there, and I don't need to go into that now. But then Rankine came along and said, wait a minute, I think heat can pass from cold to hot when you look at the universe, and he wrote a paper on this. Again, I'm not going to go into that. Clausius then came back and proved Rankine incorrect. And so he concluded in his 1865 by stating that the entropy of the universe tends to a maximum. Notice he used the word universe here, building on Rankine's earlier paper. And so Clausius introduced to us the concept of an increasing entropy. But he never declared that the entropy of an isolated system tends to a maximum. Did he truly understand that it does? I don't know. The thing that I do know is that when he summarized his work in 1879, he included no mention of a natural tendency for entropy to increase. So given that, how did we eventually transform the entropy of the universe tends to a maximum to the entropy of an isolated system increases to a maximum? Enter J. Willard Gibbs. He did a phenomenal job on taking Rudolf Clausius's work up to a much higher level. I won't go into all of the details of that here, but he did that work between 1873 and 1876. You see, Gibbs deeply understood the implication of Clausius's work, perhaps more than Clausius did. And with the specific regards to the concept of the entropy of an isolated system increases to a maximum, this is what Gibbs saw in Clausius's work. Specifically, he put mathematics to this. When he looked at the entropy of an isolated system, he said, okay, all of the parts of the isolated system, whether it's equilibrated or not, have an entropy in and of themselves, and those can be added together because entropy is an extensive property. And that can generate this S total, this total entropy of the system, and then increases to a maximum. Well, again, to Gibbs, what that maximum was this S max total. And when did that occur? Well, it occurred when the system was fully equilibrated. We'll go into details of that in a later video. But then the concept of increases led to this sign here. And this sign here occurred in Gibbs' work when he did extensive mathematics around this. But basically, the entropy of a system is less than or equal to the maximum entropy that it can get. And thus the system evolves over time. It increases to this maximum over time. I don't need to go into all of those details, but Gibbs certainly did in his work. And this equation and this mathematics pervades his work. So that brings us to the point where entropy has been discovered in 1865 on the overall timeline. Well, what comes next? Well, next comes the kinetic theory of gases, because that's the bridge that ended up in getting to Ludwig Boltzmann's full definition of entropy here. I'll get into the kinetic theory of gases in the November video and look forward to having you join me for that one. For now, though, thank you very much for listening to this talk. There's a lot of details behind what I just shared with you. I cover all of those details in my book, Block by Block, The Historical and Theoretical Foundations of Thermodynamics. Look forward to talking with you next month. Goodbye.